Hey, Nathan here, welcome back to another game algorithms video. In this video, we are going to take a look at hiding artificial intelligence. Now this concept is when we have a player object and an enemy object and some obstacles. So our enemy object has the potential to see our player. So our player needs to hide from these boxes, either here or here. So hiding AI is going to take a look at this concept where the code, the artificial intelligence, will automatically take care of hiding for us. We want the object to automatically move and position itself to where the box is obstructing the enemy's view. So let's take a look at the algorithm. Let me bring up the eraser here and I'll start erasing some of this stuff. So the algorithm. We need to find the best hiding spot, and right now the algorithm is set to whatever is closest. Our goal is to hide from our enemy as quickly as possible. Now, we might add more conditions in the future, like most efficient. A bigger box might be more efficient than a smaller box. And this example is built on the concept of a enemy that is staying put. If the enemy is moving around, the algorithm will become more complex. But for this example, the enemy is staying put. It will rotate. It might look at us. So we just need to avoid the enemy. So the main goal of this artificial intelligence algorithm is to get to a hiding spot as quickly as possible. So we need to find the best hiding spot first. So we can hide either here or here. So we need to find the closest one, which we can visually know it's this one because we can see it. That's closer to our player, and this one is farther away. So if our main goal is to get to a hiding spot as quickly as possible, we want to choose this one. So let's erase this. Okay. Let's actually erase this because I'm going to demonstrate the algorithm now. So we need to calculate a distance to box. We'll just call this a 2-box vector. So for each box, we might have more boxes here, here, here. And depending on how you want to handle this, we can pick the closest box first. But depending on how it's positioned, we want to actually pick the target location as the test. It's just depending on where the enemy is and how the box is positioned, we might want to hide here for this box and here for this box, which now this one will be the closest one. So we are actually going to loop through based off the destination location. So what we need to do is we need to first loop through every box. So we will choose this box first. We need to calculate a 2-box vector. Now that is enemy to box. So I'll just call that E to B, enemy to box vector. So remember, we are dealing with the center point of our objects are the positions. So that is the position of our box. So we need to calculate an enemy to box vector. So it'll look something like this. Enemy to box vector. So we have an enemy to box vector. Now this is a square you might have circle objects or triangle or just any other forms of geometry or just random objects in general that you want to have to block the enemy's field of view. So we need to calculate an outside of the box length as well. So our box is going to have a kind of a circle around it, and that will be used to calculate our vector for pointing outside the box. So we're going to extend this vector to the point where it's just outside the box. So we're going to extend this vector here. So we're going to use a combination of the width and the height in order to determine this circle area. Whichever is higher, this might be let me put this in blue here. We might have a triangle object here. The width is going to be much higher than the height. So in this example, it's going to look like this. So we're going to have much more leeway here than we will at this point. So let me erase that. So we use the highest value in the example that I'm erasing. That was the width, because the width, it was larger than the height. So that might cause some issues where we have a big gap. As you see here, there's a big gap here. But that's okay. We just want to get to a hiding spot. We don't care the exact where the box stops. We just need to get to an area outside the box. And then we'll have some threshold value that is kind of just some distance we want to have for the object. We are going to throw in obstacle avoidance, so we can use the obstacle avoidance distance threshold, but we will have another barrier outside the box. And then we extend that same vector there. So now this is the point we want our object to be. So that's enemy to box 1. And this is box 1. Alright, so now we found that point. This vector is relative to the enemy. This vector is relative to the enemy. We need to convert it relative to the game world. Because every object's position, let's take a look at this boxes for example. This position value is relative to the game world. So this position vector, this is B1, this is B2, B3, B4. So this is B4. So B4's position is going to look like this. This is the top left of the game world, and this is B4's position. B4 dot position. That's the position vector of our objects. We need to convert enemy to box 1 relative to the game world. So our enemy has its own position vector. So this is enemy.position. And then we have enemy to box. So what we need to do is we need to add enemy to box 1 plus enemy's position. So once we do that, we get this vector here. We will call that C vector for choice. So this is the choice vector. Now, our player has his own position. That looks like that. So that's the player's position. The next thing we need to do is we need to calculate the length from the player's position to the choice vector. So we need to calculate this here. And we just need to get the length. So to get length, that's the length vector. So to get the length vector, that is equal to the choice vector minus our player's position, that vector. So that will give us our length vector. And we just want to get the square of the length. We don't care about the exact length of the vector. We just want to see if it's less than the other one. So right now, this is our first test. So this is going to be the closest box because it's the only one we have tested against. So we have chosen this box. Now we will store that squared length. We will store this and save this, the squared length of our vector. And then we will test this next. Then we will repeat the exact same process we did above. So we will repeat the process. And then we will compare the stored length squared with the new test results, with the new, let's say new tested boxes squared L. If new one is smaller, update the choice. So if this box has a smaller squared length, we will then choose this box as the target because it's closer. So we will test this for all boxes, and then we will seek to our desired choice vector. Now you can speed this up and sort the boxes by their proximity to the player. But like I said, depending on where the enemy is located, a closer box might not be the one we want to move to. Because our goal is to get to the closest point where our player is being obstructed by the enemy's view completely. So we use that E to B vector here. We use that E to B vector to determine the correct 100% blocked view from the enemy. If the enemy is looking directly at that box, 100%, that is where this point comes from. So it will be looking at that point directly, and if our player is there, the box is going to be obstructing the view. Okay. So let's delete this. So that's a basic concept, and this is going to be part 1. For part 2, we're going to make things a lot more complicated, but this will give us a step in the right direction for hiding AI. For example, we have a massive player object, and we have some enemy here, like a turret or something. We have a very small box here. We have a very large box here. We know that's not going to work. That's not going to obstruct the enemy's view. But the algorithm won't know that. So this is what we will cover in part 2. In part 2, we will take a look at the object's size and determine if our size matches the needs of our box's size and things like that. But for this initial first dive into hiding AI, we're just going to simply assume that all boxes are the right size, they are appropriate for our hiding spots, so we just need to pick one. And also for part 2, we're going to determine if it's even necessary to move. For example, there might be another box here. We know that's already obstructing the enemy's view, so we don't need to move at all. But for the part 1 algorithm, it will try to move. That will probably be the closest one. It will try to move there. Alright, so this is a very basic concept. We just need to loop through every single box or every single object that we can use to obstruct the enemy's view. We need to calculate an enemy to box vector. Let me just redraw a whole bunch of stuff here. So we loop through every single box. We loop through, we choose this one first. Okay, we tested that one, then we choose this one. Alright, so we loop through every box. For each loop, we need to calculate an enemy to box vector, which looks like this. Enemy to box vector. Then we need to get outside the box, and you can go directly to the obstacle avoidance threshold if you want. That way you don't have to calculate directly to the box's barrier. So let's say our obstacle avoidance threshold is something like that. So we need to extend this E to B vector to where it's on that threshold line. So now this is the E to B vector. Next, we need to convert that to relative to the world, not the enemy. So to do that, we need to convert it to where it looks like this. And we will call this our choice vector. So our choice vector is going to equal enemy dot position plus E to B vector. So we just add those two vectors together, and that will give us our C vector here. Now, we need to calculate a length from our player to that choice vector. So that will give us our length vector. So length vector is equal to our choice minus our player.position. So that gives us our length. Now, we just need to know the distance. And we don't need to know the exact distance. We just need to know some distance. So we're using length squared because that is more performance than getting the square root and finding the actual length of the vector. The reason we're doing this is because when we test one box to another box, we just need to know if it's closer. We don't care if one box has a distance of 2 and one box has a distance of 1. If we get the squared, which is 4 and 1, that's the same thing. 1 is still closer, even though it's the squared value. So there's no reason to do the square root in order to just test between one and the other. If one is closer than the other, we don't care about the actual value. We just need to compare the two. So that is why we're using the squared value. So if that length squared is less than our current choice's length squared, then we update our choice because the new one we tested is now closer. Right now, this is the first one we tested, so we choose this one. So let's call this C0. So this is our current choice. I'll just call this current closest. Current closest. Okay, so now we do the same thing for this box. Let's test this box now. So now we need to calculate an E2B E2B. So now we need to get outside the box, which will be now like right here. And then we convert that to the world, which will be this. And that's C1. And then we calculate the length between our player and that value. And that will be L1. And then we calculate L1 squared, the length for that, and then compare to the two. We can visually see that L0, the first one we tested, is closer than L1. So this will still be our closest choice. So we'll still move to that box. Alright, so this is hiding AI. This is the basic implementation of hiding AI. We will extend on this to look at the box's size. I keep on saying boxes, but they can be any object, any barrier that we can use to obstruct the enemy's field of view. So we will look at the size of the objects and determine if it's suitable for us to use, and we will also include a check to see if we actually need to move. Alright, so that's it for this video. I hope you enjoyed it. Next video we will discuss field of view. Thanks for watching.